Okay, so in this video we're going to be talking about the laws of thermodynamics. So just like you have Newton's 3 laws for motion, the laws of thermodynamics basically govern the realm of heat and thermal energy. Okay, so remember in the last video we talked about things like, thermal energy, temperature, pressure, thermal equilibrium, all that good stuff, looked at that simulation. And so now we're going to talk about the laws of thermodynamics, and there's only 2 of them. Okay, so the first one is basically essentially the conservation of energy. Okay, but it's written in a different form. So remember, the conservation of energy says that energy cannot be created or destroyed, but it can be transformed into different forms. Okay, now the way we use the conservation of energy, or the first law of thermodynamics in this unit, is we use it as an equation that looks like this. Okay, and the equation is Q equals W plus delta U. And we will go over this on the next slide when we talk more about the first law. Okay, but this is the first law of thermodynamics. Okay, so again, we'll talk more about it on the next slide and do some examples with that. The second law of thermodynamics can actually be written one of 3 ways. Okay, so here are the 3 ways. I will underline the 3 ways for you, okay, because they're all kind of grouped together in this bullet point. Okay, so the second law of thermodynamics says entropy of a system always tends to increase. Okay, now tends to basically means naturally. Okay, so entropy of a system always naturally increases. Now at this point you might be wondering, wait, what is entropy? Okay, I'm guessing you've probably never heard that word. That's fine, we will talk all about entropy here in a little bit. Okay, but entropy of a system always naturally increases. That's way number 1. The second way to state this second law of thermodynamics, is to say that heat tends to flow from hot to cold, okay, on its own. Now again, when I say tends to, I mean naturally. That means if you have something that's hot and you put it in a room that's colder, the heat is naturally going to flow out of the hot object and go into the colder object. Okay, so that's the second way to write the second law of thermodynamics. Okay, now, way number 3. You cannot have a 100% efficient machine. Okay? A 100% efficient machine can never be built. In other words, the efficiency of a machine always has to be less than 100%. Now, again, at this point, you might be asking, what does that mean, efficiency? We'll talk about that in a little bit. Okay? One of the consequences of the laws of thermodynamics is that it's impossible to create what's called a perpetual motion machine, which is basically a machine that creates more energy than it uses, or a machine which runs forever. Okay, so I will link these 2 videos. They're just kind of for entertainment, but definitely check those out. Okay, so pause it here if you need to look at that some more. Let's focus more on the first law of thermodynamics. Okay, so the first law of thermodynamics, here it is. We write as Q equals W plus delta U. Now, W we saw in the last unit, W is work. Okay, so in this context, W is the work done on the surroundings. Okay, now when I say surroundings, well, I'll explain in just a minute. Q is a symbol for heat. I don't know why we use heat for Q, okay, but we do. Okay, so Q is heat, W is work, and then delta U is what's called internal energy. Okay, so delta U is a symbol for internal energy. So basically, heat equals work plus change in internal energy. Now, what does that mean? Okay, here's what that means. When you add heat to a system, okay, remember that's Q, that heat can go to one of 2 places. Either it can be absorbed by the system, okay, that's the delta U, or it can go to doing work on the surroundings, meaning it can cause something to move. Okay, let me give you an example. Okay, let's say you take a balloon and you heat up the balloon. Okay, either the air inside the balloon is going to get hotter, or work is going to be done and the balloon is going to expand and get bigger. You might have seen that before, where if you take a balloon and you heat up the air inside of it, the balloon expands. Okay, when it expands, that is work being done. Okay, so in other words, when you add heat to the balloon, either that energy is going to go to making it expand, or it can also be absorbed by the gas inside, and the gas just gets warmer and increases in temperature. Okay, so that's basically what the first law of thermodynamics says. Okay, so we're going to do a few examples with this. Pause it there if you need to look at this equation, write that down. Okay, so example 1. Example 1 says, consider a rigid unbreakable steel can of air. You heat the can from underneath with a Bunsen burner. What happens? Okay, so if we have a can filled with air and the can is rigid, that means it's like really hard and it's unbreakable. That basically means that when we add heat, if the can can't move because it's unbreakable, then think about the first law of thermodynamics. Okay, it says that Q equals W plus delta U. Okay, so if we're saying that it's a really hard, unbreakable can, if it can't move, if the can can't expand, then the work done has to be 0. Okay, so how would we answer this question? Okay, I would say, I'm going to do this in red, as heat is added to the can cannot expand, and so the heat is all absorbed by the air in the form of internal energy. Okay, in other words, the air inside the can gets warmer. Okay, so let me make that red so you can see that a little bit better. Okay, so in other words, we're adding in Q, W is 0 because if the can cannot move because it's unbreakable. Remember, if an object cannot move, there's no work being done. Now, let's suppose that the top of the can is free to move. As you heat the can from underneath with the Bunsen burner, what happens now? Okay, well, now the can move, at least the top can move. Okay, so as heat is added to the can, the pressure in the can will increase and cause the top of the can to to expand. Okay, so now the top of the can move, it can go up as the can is heated, and so now work is being done as we add heat. And so that means if work is being done, that means not as much energy is being absorbed in the form of internal energy. Okay, now, if this is all too abstract, think about, like, I don't know, a soda can. If you take a soda can that's not open and you heat it up, eventually what's going to happen is the can is going to explode because all that pressure builds up inside, and then, well, work is done when the can explodes because the force is acting over a distance. Okay, so in the first question, it was basically like a soda can that's made of something indestructible that can't break, which means all the heat has to be absorbed by what's inside the can. And in the second question, it's basically like a real life soda can that can actually move and expand and deform and stuff. Okay, so that's kind of a concept question. Let's do some calculations with this. Okay, pause it there if you need to get that down. Okay, so example 2. Example 2 says a cylinder holds an ideal gas at room temperature. 1,000 joules of heat is added to the gas. Okay, now, first of all, 1,000 joules of heat. Remember, heat is Q. How much heat is absorbed by the gas? Okay, so the heat being absorbed by the gas is going to be our delta U. Okay, that is our unknown. When it does no work on its surroundings. Okay, so if no work is being done, that basically means the work done is 0. From the first law, we have Q equals W plus delta U, and it's basically saying Q is 1,000, W is 0. Okay, so how much is being absorbed? Well, obviously, delta U is going to be 1,000 joules. That means all of it is being absorbed since none of it is used to do any work. Now, in the second question, it's basically the same question, except now 1,000 joules of heat is being added. Okay, so that's Q. How much heat is absorbed by the gas? So same question. Okay, but now it says 300 joules of work is done. Okay, so same question, just different numbers. And now they're saying, okay, Q is 1,000. What if W is 300? So I'm going to plug in 300 for the work done. How much is actually absorbed by the gas? Because remember, when you add heat, either it can go to doing work or it can be absorbed by the gas. Okay, so what plus 300 makes 1,000? Okay, so if you subtract 300 on both sides, you get 700 joules. Okay, and so you see calculations with the first law tend to be very, very, very basic and easy. Pause it there if you need to look at that some more. Okay, I'm going to erase this. And example 3 says 400 joules of heat is added to soda can, which does 250 joules of work as it expands. Okay, so this is the soda can thing we talked about before. Alright, okay, so 400 joules of heat is added, that's Q. We have the work done is 250 joules. Okay, so Q equals W plus delta U, and we want to know how much heat was absorbed by the gas, so we're looking for delta U, that is our unknown. I plug into my equation, Q is 400, W is 250, and to get delta U, I'm just going to subtract 250 on both sides, and the heat absorbed by the gas, delta U, is going to be 150 joules. Okay, so there you go. That is example 3. And then state how this added heat will likely change the pressure of the air inside the can. So remember, pressure has to do with how often those gas particles collide with the container. Okay, so if heat is being absorbed by the gas, 150 joules is absorbed by the gas, that means those gas particles are going to increase in temperature. Now remember, temperature is a measure of the average kinetic energy of the atoms or molecules making up an object. Okay, so what's going to happen to the gas inside the can? Well, it's going to heat up. That means the temperature is going to increase. That means those gas particles move faster. And if they move faster, that means they collide more often. And so how is this heat going to change the pressure? It's going to cause it to increase, which you probably could guess on your own. Okay, so pause there if you need to look more at example 3. Okay, so the second law of thermodynamics, remember there's 3 ways we can state it. Basically, either heat always flows from hot to cold naturally. Now I say naturally, we can force heat to go from cold to hot. Okay, we just have to, make a machine that does that. That's something like your refrigerator does that, or your AC does that. Okay, it uses a motor to basically force, to act as a heat pump, to basically force heat to go from cold to hot. But on its own, naturally, heat flows from hot to cold. Okay, that's kind of, self-explanatory. Now, let's talk about this efficiency thing. So the second law basically says you cannot reach 100% efficiency. Okay, so what is efficiency? Efficiency can be calculated as basically output over input. Okay, so E, lowercase e for efficiency, is output over input. And typically efficiency is given as a percent, which means that really it should be output over input times 100. Remember, to go from percent to decimal, you have to divide by 100. Okay, so just keep in mind, if you're given the percent and you want to do a calculation with that, then you have to convert from percent back to decimal. So basically, the second law says that the output must be less than the input. You cannot get 100% efficiency, okay, because there's always some type of friction that removes energy from the object or from the system. Okay, so you cannot reach 100% efficiency. So let's do a quick example with efficiency. Okay, so remember, efficiency is output over input. Okay, so E equals output over input. And it says a certain light bulb consumes, remember consumes means uses up, 200 joules of electrical energy per second. Now, by the way, 200 joules per second is 200 watts. We talked about, power before is energy over time. Okay, so 200 joules per second is 200 watts, but it doesn't really matter here. But it only emits, okay, that means puts out, 25 joules of light energy per second. Okay, or 25 joules or 25 joules per second, or 25 watts. What is the efficiency of the bulb? Now, the good thing about efficiency problems is there is a very easy way to tell if you made a mistake, because you cannot have an efficiency more than 100%. It is physically possible to have more output than you have input. So that means if you do an efficiency calculation and you get a number bigger than 1 or bigger than 100%, you messed up. Okay, so the output is going to be 25 and the input is going to be 200 just from reading the problem. Okay, plus if I got those switched, I would end up with more than 100%. Okay, so the top number always has to be less than the bottom number. So the efficiency, 25 over 200, if you put that into the calculator, comes out to be 0.125, or as a percent, if you multiply by 100, you would get 12.5%. Okay, so that is the efficiency of this light bulb. Okay, it emits 25 watts, 25 joules per second of light, but it actually uses 200 joules per second. Okay, and of course you know when you pay your electric bill every month, this is what you're paying for. Okay, so it's in your best interest to get really efficient light bulbs so that you don't have to pay a high electric bill every month. All right, let's do one more example. Okay, example 5. It says a crane uses 120,000 joules of energy in order to lift a 500 kilogram motorcycle up 8 meters off the ground. Calculate the efficiency of this crane. Okay, so this is actually a little involved calculation. So basically it's saying it uses this much energy and it's lifting a motorcycle. Now look at what we're given. We're given a mass. Okay, this is a mass and this is a distance. Okay, what does that make you think of? We did a lot of calculations using work and the work equation. Okay, remember work is force times distance. Okay, to lift the 500 kilogram motorcycle, remember to find the force, that would be mg, and so that would be 500 times 10, which is 5,000 joules, or 5,000 newtons. And then if you use the work equation, you do 5,000 times 8, okay, then you get 40,000 joules. Okay, now what does that have to do with the problem? Well, this basically means that the output of the crane is 40,000 joules. That's how much energy it takes to lift the motorcycle 8 meters. So that means this is basically the output. This is going to be the input. And remember, efficiency is output over input times 100 to convert to percent. So that would be 40,000 divided by 120,000 times 100, okay, which is, if you round, is about 33.3%. Okay, so approximately 33.3% is the efficiency of this crane, which is pretty good. Okay, so pause it there if you need to look at that. I want to move on to entropy. Okay, I am going to skip example 6. See if you can figure out example 6 on your own. If you just move this text box, it should have the answer below this text box. Okay, so remember the last way to state the second law of thermodynamics is about entropy and how the entropy of a system always tends to increase. That means it always naturally increases. Here's what entropy is. Roughly speaking, and I will bold it and put it in red, entropy has to do with the amount of disorder in a system. Okay, when you talk about disorder, you're basically talking about how organized something is. Okay, so let's take a look at an example. In which of the following situations is not a situation which would lead to an increase in entropy? Okay, so if you sort a package of M&Ms into different piles based on color, remember, entropy is a measure of disorder. So think about organization. If you take M&Ms, which come, all the colors come together, and you separate them based off of color, are you making the M&Ms more organized or less organized? Well, you're making them more organized, which means this would be a decrease in entropy. Okay, that second one. This would be a decrease in entropy because sorting the M&Ms, you're going to decrease entropy because you're decreasing the order, because you're sorting by color. When you shuffle a new deck of cards, guess what? You're increasing the disorder. That's an increase in entropy. Okay, why? Because when you buy a deck of cards, all of the cards come in order. Okay, so if you shuffle them, they're going to become more disordered, less organized. Okay, so that's an increase in entropy. Okay, heating up a container of air. So if you heat up a container of air, the air molecules are going to move faster. And if they move faster, that means they are less organized. So this is also going to be an increase in entropy. And melting a block of ice until it becomes a puddle of water. Okay, well, if you think about a block of ice, ice is a solid, and so all of the water molecules are like closely packed together and they're nice and neatly arranged. When ice melts, those water molecules start to pull apart and become a liquid. And so that would also be an increase in entropy. Okay, and so the answer to this question would be B. Okay, sorting a package of M&Ms into different piles based off of colors. When you if you're still confused by entropy, here's another way to think of it. Think about your bedroom. Okay, let's say you clean your bedroom one day. If you go a week and, look at your bedroom again, your bedroom is probably going to be messier 1 week later, just, from living your life. Okay, that's a situation where the entropy of your bedroom naturally increased. Now, can you decrease the entropy of your bedroom? Yeah, of course, you can clean your room, but it's not going to happen on its own. Okay, so entropy of a system always naturally tends to increase. I'll give you one more example. Okay, so let's say you take a glass and you drop the glass on the ground and it shatters into a million pieces. Okay, that's a situation where the entropy of the glass increased because now all those glass pieces broke apart and they flew through the air and now they're not like together anymore. Okay, now can you put the glass back together? Sure, okay, but you would have to do work to do so. On its own, the entropy of the glass increased because it became more disordered after it broke. Okay, so that's basically the last way of thinking of the second law of thermodynamics. Okay, the entropy of a system always tends to increase. Alright, I believe that might be it. This is just some things we talked about before. As always, please let me know if you have any questions, and I will see you guys in the next video.